So in this chapter we will be starting about inductance, and after that we will go into mutual inductance. Now first let us understand what is inductance. We know with a change in magnetic flux with respect to time there is a directly proportionality of change in current with respect to time t. So this is what we know. That is, if we change the magnetic flux, the current produced will keep on changing. Now, in a way, one particular coil gives you a magnetic flux. So, n number, this is the n number of coils. N number of coils, that the change in n number of coils with the change in magnetic flux. Now, if this is a change in magnetic flux and if there is n number of coils, then n into the change in magnetic flux or flux can be understood as a direct change in current. So the number of turns in a particular wire, if we increase, in each wire a current will be generated. So if the number of turns in the wire is more amount of current will be generated. So in a way, the number of turns into the magnetic flux is directly proportional to the current so produced. This is the current. This is a magnetic flux. Magnetic flux, and this is the number of turns. So this is a proportional. So if we take this to be equal, so we have to introduce a proportionality constant, and that proportionality constant is known as your inductance. That proportionality constant for this particular case is known as your inductance. So how much induced current can it produce is known as your inductance, and this is given by the formula N into phi is equal to, this is the current I and this is the M. Now this M is for mutual inductance. This M is for mutual inductance. Now, depending upon the situation, there are two types of inductance. One is mutual inductance because of two mutually varying electric field and magnetic field. The current so produced is known as your mutual inductance. The other one is your self inductance. Now, depending upon the situation, whether this constant will be mutual or this constant will be self will be determined. But the constant itself is known as your inductance. So let's have a look at our first step, that is of mutual inductance. So now let's understand what is mutual inductance by taking two solenoids. Now, one solenoid is of a small radius r. So this is one solenoid with a small radius, say r1. This is a small radius. Now we will keep, so the number of turns in this particular solenoid be n1. Again we take a bigger solenoid that is coaxial with the inner solenoid, that is they have a similar axis, coaxial. So this is my bigger solenoid. Let me draw this with a different color. So this is my bigger solenoid. So let the radius of this be R2. This is R2. And the length of both the solenoid be L. That is the length. Now, say suppose the corresponding quantities of the outer solenoid S2 are R2 and N2. If this is the outer solenoid S2 and this is the inner solenoid S1. So similarly, S2 and R2 and N2. So the number of turns over here be N2, and for the inner solenoid is the number of turns is N1. The radius is R1. So we have established this particular situation. So now, if you look at the second solenoid, that is the above one, if I pass a current I2 in the bigger solenoid, if I pass a current of I2 through S2, it is in turn sets up a magnetic flux of S1. So if it produces a magnetic flux, produces a magnetic flux, produces a magnetic flux, and that magnetic flux that is produced passes through S1. It passes through, let's write this, it passes through S1 because it generates a magnetic field. So the magnetic flux passes through this particular solenoid S1. So let the magnetic flux that is generated thus be phi 1. Magnetic flux, that is the total field line that passes through the solenoid S1. Let that be phi 1. So now if I link the corresponding flux linkage with solenoid S1, so the total flux S1, because of the number of turns N1, that is the change in flux, is actually equal to mutual inductance M of 1 because of 2. Now you have to keep in mind, I have written M of 1 because of 2 into the current I2, into this current I2. This is the current that has been passing over here. Now, if you are getting confused what is M12, when the first term which comes, that is the mutual inductance of solenoid X S1, mutual inductance of solenoid S1. So what is the inductance of S1 because of solenoid S2. So this is what it is given. Now similarly, what we can find is that this is the mutual inductance. Now the magnetic field due to the current I2 is actually given by, if you look at the magnetic field because of I2, say this is the current I2 that has been passed over here in solenoid S2. So the magnetic field that has been produced is mu naught into N2. What is the magnetic field? That is the number of turns into mu naught into the current I. This is I2. So this is the magnetic field that has been produced. So now if you put this value over here, then what we will find is that this N1 phi 1 is actually equal to N1L upon pi r square 1, because the area, into mu naught N2 I2. So this becomes mu naught is a constant term, N1 N2 is a constant term, and pi r1 whole square is a constant term into L, that is the length of the solenoid, which is also constant term, into I2. So this is what is given into I2. So now what we can say is, the mutual inductance M1 because of 2 is nothing but your mu naught N1 N2 pi R1 whole square into L. This is the mutual inductance of 1 because of 2. Similarly, what you can say, if you look at the mutual inductance because of this current over here, we will find that M2 of 1 will be given by now let us take N2 phi 2 is equal to M2 of 1 into the current I1 that is flowing over here. The current I1 that is flowing over here. So N2 phi 2 is actually given by N2L pi R1 whole square into mu naught Ni I1. So if you look at M21, what you will find is mu naught Ni N2 pi R1 whole square into L. So in a way, we can now come to a conclusion that M1 of 2 mutual inductance because of 1 of 2 is same as mutual inductance because of 2 of 1, and this is a very important relation that we can derive or understand.